web page. But again, a quick reminder, before you submit a report, please form your group. Even if you had formed a group for the video, even if you formed a group for the report, it doesn't carry over. So you have to go through the entire group formation process in AutoLab all over again. I think a bunch of you have already provided feedback, so thanks. And I said sometime later this week I'll probably summarize and give some comments back. But if you have not done so, please go ahead and give feedback. Are there any questions on logistics? All right, so we were looking at divide and conquer algorithms. So in particular, we looked at the merge sort algorithm to solve the sorting problem. And here's kind of like the three-step process for divide and conquer algorithms. You divide your origin problem into two or more sub-problems. I need to clarify, when it's a sub-problem, it's essentially it's exactly the same problem, but on a smaller input size. Then you recursively solve these problems and then patch up the solutions from these smaller solutions to give the solution for your original input. And typically, this last step is where all the work happens. And as I think I'd mentioned this briefly last time, but again, as a reminder, again, this is not a theorem. It's just something that's typically true in what we'll see, at least in this course. Is the greedy algorithms we have seen, the kind of naive algorithms or brute force algorithms for exponential time, and we're saying using greedy algorithms you can bring it down to polynomial time. Right? So there is a huge improvement in runtime. In typical divide and conquer algorithms, the improvements are a much smaller scale. So it's like something like n squared goes to something smaller. Right? So if we were to do sorting using bubble sort, insertion sort, or selection sort, you have n squared, but using merge sort, you get n log n. Okay, so all the examples that we'll see in this course on divide and conquer would be going from a larger polynomial runtime to a smaller polynomial runtime. In most cases, the smaller polynomial runtime is something like n log n. So you actually bring it down really close to the input size. So the problem we are going to look at today is something that you guys have seen before, like multiplying two numbers, two integers. That's something very basic. However, unlike how we have been treating numbers so far, so for example, if they were edge weights and things like that, we assume that they're small enough so that the entire number can fit into one register, or even constants in many cases. But now we're looking at numbers that are really large. And so what you're given are two large integers in bit representation. So you have an minus 1 to a0, bn minus 1 to b0, and you want to compute the product. If you look at the elementary school multiplication algorithm that you've done, you just take b0, multiply it with everything else, then multiply with b1 and shift, and so on and so forth, and then you add column wise. That's n squared, because you have n such rows and you're spending O of n time on each one of them. So what we're going to, so I think, I forget where we were when I asked this question last time, so let me re-ask. How much do you think you guys think we can improve from n squared? So I'm guaranteeing you will go down much better than n squared. Alex?
Is it O of n?
It would be great if it were O of n. No one knows how to do O of n.
N log n?
It would be great if we know how to do n log n. We still don't know how to do n log n. But we are very close to n log n. So I'll probably post something on Piazza to that effect. However, in class, we are not going to get anywhere close to n log n. Okay? What we're going to do is replace 2, n squared, that 2, by something like 1.59. Okay, so we're going to make it much faster asymptotically than n squared, but it's nowhere close to n log n. All right. Mark, did you have a question or comment? No, that's right. Okay, so that's a point I should have clarified. Whenever we talk about algorithms in this course, there's no pre-processing, right? So you get the input, And the moment you get the input, your clock starts. Right? Pre-processing, when you have this table of all possible answers pre-computed, is not allowed in this game. However, there are lots of fascinating questions on what happens if you start allowing not exponential time pre-processing, but let's say I allow you polynomial time pre-processing. Can you do things faster? And the answer is yes. And then the trade-off becomes, how much pre-processing time do I allow you, and how much improvement do you get in the actual run of the algorithm? But unfortunately, won't have time to go into that in this course. Any other questions, comments? All right, so the kind of algorithm we are going to do is one of my favorite kinds of algorithms. It's an algebraic algorithm, right? So we're just going to deal with symbols. I love it. Unfortunately, it becomes a bit dry. So what I'm trying to do is we're going to work through the algorithm. I'm going to have a running example that hopefully at least illustrates the identities that we're doing. And as a kind of preview of what's going to come, I will put out an identity that will literally come out of nowhere. Okay, it's a very simple identity. I'll show it to you. You will all agree that it's true. But the most natural question that always comes is, but how the hell did someone come up with this identity? So I will also post something on support page that will partially answer that question. Okay, but anyway, yeah, let's get started. All right, so I say we are trying to multiply two, and I say I want to clarify it's large integers. And so my input are two numbers, A. So the n minus 1th is my most significant bit, and A0 is my least significant bit. So as you probably have seen this multiple times in many of the starting courses, if you were to look at what is the decimal equivalent of this number, which I'll call dec of A, is just summation of I from 0 to n minus 1 of AI times 2 to the I. Right, and so this is essentially the algorithm to convert your binary into decimal. We're also given another number B, and of course this expression has nothing specific to A, but just to kind of write it down explicitly. You can also get the decimal equivalent of B by using the same formula. And you want to output C, that's the product of A times B. And I'm just going to use this kind of tiny dot that's filled in instead of a cross to denote the product. All right, so for example, my A say is 1101. And this is the binary equivalent of 13. And B is say 0011. And this is the binary representation of 3. And so just to make sure all of us are on the same page of when I said, let's look at the elementary school algorithm. So if you were to do the elementary school multiplication algorithm, so you write down your A first, and then you write down your B over here, then you multiply this with all of these guys, write that number down, so 1011. Do the same thing over here, but then shift by 1. So 1011. Then you do 0, so you get all 4 zeros, but it's shifted by 1, and another 1, you add it up, 1 1 1 0 0 1. And if you work out the decimal equivalent, it's 39. We know that has to be the case. And so this is an n squared time algorithm because computing each row takes O of n time. Okay, so computing each row is O of n time, and so overall it's O of n squared. So even the addition takes n squared time. So you have these columns of length n, you have to add n bits together. Sorry, I keep on forgetting name. Brandon.
I just like confused about this middle step here. Like, what are you doing there?
So when you multiply these numbers, right? So you take one bit or digit of b, multiply it with everything that's a, and then every time you move ahead towards the more significant bit of b, you have to keep on shifting. Any other questions? So any questions on the problem statement? Any questions on this algorithm or why it's O of n squared? Okay. All right, so our goal is to beat this O of n squared algorithm, and as I said, we're going to look at divide and conquer algorithm. So if you remember, the first step in divide and conquer is you want to divide it up into smaller subproblems, right? So what would be the most natural way of creating subproblems given these two numbers a and b? Evan.
I mean, it's you multiply each digit of b, sort of like each bit of b by a.
Right.
And so I mean, like that's like where you can really divide them.
Right. So the idea is, one of the reasons you get O of n squared is you're using each bit of b to multiply with a. Right, and that's already n and the name n of those guys. So the idea is, let's just divide up b into 2 halves. Right, so you have two numbers which are now roughly n over 2 bits, but it turns out to make everything work, you might as well just divide the a into 2 halves too. So we're going to divide both a and b into half. And when I say half, I mean look at its binary representation, think of that as an array and just literally break it into half like we did for Mozart. So the step 1 would be divide a and b into 2 equal halves. So what do I mean by this? Well, so my a is, again, if you think of it as an array, has n bits from most significant to least significant. Let's just look at the last ceiling of n over 2 bits, and then you look at whatever is remaining, so n minus ceiling of n over 2 bits. And I call this part, which you can't see, as a, so I'm going to distinguish between subscripts and superscripts. So subscripts are bits, superscripts are halves. So a superscript 0 is the last half, a superscript 1 is the first half. More precisely, a of 1 is a of n minus 1 all the way up to a of ceiling of n over 2. A of 0 is basically the remaining bits, right? Or like the least significant ceiling of n over 2 bits. So So let's go back to our example again. So I'm using the earlier examples now. A was 1101, and so in this case, A1 would be the first 2 bits. N is even, so n over 2 is n is 4, so n over 2 is 2, and A superscript 0 is 01. And so in this case, the decimal equivalent of this is 3, and the decimal equivalent of A0 is 1. Okay. So now let's do a quick kind of mental exercise, and I'll tell you shortly why we are looking at this. So let's say I want to write 13, which is my original decimal equivalent of my original number, as an expression that has 3 multiplied by 2 with a power that I want you guys to figure out, plus 1. So what should be in the power of 2 to get what I want? Alejandro? 2, right? Which in this case turns out to be exactly n over 2. So you replace this guy is actually a 2. And it turns out this is not a coincidence. You can prove that this will always hold in the following sense. So here's the claim that I want to make. So I claim that if you look at the number A, or I'll explicitly write it in terms of decimal A just because I want to use its decimal expansion while proving this. This is same as the decimal equivalent of A1 multiplied by 2 to the ceiling of n over 2 plus the decimal equivalent of 0. Okay. So now if you look at this expression, this is exactly what you get when you replace n by 4 in this case. Okay. Maybe I'll stop for half a minute, talk to your friends, let me know if any questions on notation or not. Otherwise, the plan going forward is I'm going to quickly argue why this claim is true, and this will just follow from the definition of binary representation. And then what I'm going to do is substitute this expression for A, substitute similar expression for B, and then come up with an expression for A times B in terms of products of this A1, A0, B1, B0, right? So I'm going to reduce a problem of multiplication over n bits to a couple of or few problems of multiplication of n over 2 bits. But before I go any forward, I want to make sure all of you are comfortable with the notation so far. So talk to your friends for half a minute, let me know any questions. If not, we'll move on. All right. Are there any questions? Everyone okay so far? Okay. All right. We'll go ahead and prove this. Is not that hard. We just have to use our definition of the decimal equivalent and kind of do some simple symbolic manipulations. All right, so the first thing to note is just remember that the decimal equivalent of A1 would be, if this were the least significant bit of A1 and this is the most significant bit of A1, what is the corresponding decimal value? So it's I from so again, I'm starting from this index, so I'm just indexing I from here. So it's AI times 2 to the I, but then I have to subtract off an n over 2, because when I is n over 2, then this is my least significant bit, so it should get multiplied by 1. Right, so for example, if you had, right, and so sorry, let me just write down probably I should have started over with it. The easier one is when you're looking at I from 0 to, okay, so this is just saying, look at the binary representation of A0, which is this guy, then apply the formula for converting to decimal number. N is the number of bits. N is the total size. Right. So all this is saying is, again, it looks a bit odd, but the moment you have to do this correction, because when you're looking at just this number, which has roughly n over 2 bits, right? And this has to be least significant bit. So if you look at, okay, so let me write this down. So decimal of A1 is this guy multiplied by 1. Right, plus the next guy multiplied by 2, and all the way up to A of n minus 1 multiplied by